Okay, brief description of the purpose of Idaho Avionics. The value proposition. I see DIY electronics and experimental aircraft having a big overlap that would be hackable avionics. So DIY electronics, this is the Raspberry Pi and Arduino crowd. And then experimental aircraft, these are people who own like a Kit Fox airplane or a Super Cub. And then hackable avionics, the instruments in the aircraft, making them hackable so that you can customize them, make them do what you want them to do. So the goal here is to create an electronic flight instrument that is reliable, including battery backup and fault detection, that is hackable, that is, the software is open source and you can change it, that is extendable. We'll use common standards like CAN, Wi-Fi, and Bluetooth. It'll be affordable, and I'll show you what unaffordable looks like or what the contrast looks like. And it needs to look good. It needs to look the quality outside that it is inside. A little bit about flight instruments. These six on the left are commonly called the six pack: airspeed indicator, attitude indicator, altimeter, turn coordinator, heading indicator, and vertical speed indicator. The instrument on the right is the magnetic compass. So together, these form the basics of most avionics packages in an airplane. The required instruments is far fewer than this. There are only, I think, three of these that are actually required to fly. It's called Visual Flight Rules, VFR. Electronic flight instruments are different to, let's go back to mechanical flight instruments. So mechanical instruments are driven by mechanics, things inside of the instrument that are moving around, gyroscopes and little bags of air that inflate and deflate with barometric pressure and things like this. Electronic flight instruments are almost solid state completely. They are computers. Uh, and they're smaller, but they give more information. And in some ways, they're less reliable. In some ways, they're more reliable than mechanical instruments. So the package of electronic flight instrument sensors I will refer to as ADAHRS. That's Air Data Attitude Heading Reference System. Basically, the signals that you get from the six pack and the magnetic compass in the mechanical instrument world. Okay, moving on. Some non-flight instruments: engine monitoring, navigation. That's mostly, I'm thinking of maps there, and GPS, communication, and other things, autopilot, clock timer. So I'm not excluding non-flight instruments, but for now I'm focusing on just flight instruments. Let's talk about three existing products in the market. This one is produced by Avionics, called the AV30. Costs almost $2,000, and a battery is included, a battery backup is included. And you can see on the right here, there's a pitot and a static barometric pressure ports. I believe the middle port is CAN, and then uh, behind the cover would be where the battery is, and I think that might also be where you can plug in an external uh, temperature probe, a thermocouple. High quality, you can see the display is round-ish. It's round with the top and bottom lopped off. This one happens to have three kind of buttons and one knob. All of the whole display and the interface fits inside of the circle. There's no cutout at any corner. This product is made by Garmin, called the G5, a little bit less money than the AV30 at $1,655. Also, 8 hours in GPS. Uh, does not come with a backup battery. You have to buy that separately. And the back view over here on the bottom right, um, you can see that there's the pitot and the static ports. There's a place for battery backup. There's a CAN interface. And then on the front of the display here, you can see there's one knob and a button, and then there's a power button on the left. Garmin generally known for quality, but also price, relatively high price compared to other brands. And finally, this one's called the Canardia Horus. Canardia is out of Eastern Europe. They are a relatively low price brand. They're not very common in the United States, more common in Europe. And you can see from the back interface, again, pitot, static, uh, can. They have the outside air temperature probe port labeled there. And then there's a GPS antenna. So the GPS receiver is built in. A little over $1,200 for this, and the backup battery is included in this product as well. Where the Garmin is a square display that fits into a round hole, the Canardia is a round interface that fits into a round hole, but you can see that it doesn't fit perfectly. There is a knob sitting in one of those screw holes. Nothing wrong with that. I just mean to point it out as a reference. Also, again, the almost round display there. So what I'm proposing is called Product A, that'll be Product B and C, a round flight instrument. Functions like any of the six-pack flight instruments or more than one at a time. When more than one of these are installed in an aircraft, they will communicate with each other and uh, do fault detection. You can control the whole thing with a dual concentric knob, push button in the middle, and I'd like the entire display to be one round circle. I think that would look really cool. We'll include audio output for mostly for warning tones, stalls, and things. The software will be updated via Wi-Fi and web browser. That part will be pretty basic, pretty simple. Turning things off, turning things on, putting things in order. And then the external connections list DC power, pitot-static, and a third pressure sensor to collect angle of attack. Um, that's just an added benefit that it fits, so why not? Thermocouple, I'm thinking we'll instead use an I squared, what's it called, a one wire digital temperature sensor. It doesn't matter. We have the audio out as I mentioned, and then Wi-Fi, Bluetooth, and CAN bus. The user interface, as I said, should be a round 3-inch LCD, should be bright, should look solid, should look like something that you paid $10,000 for. Those knobs need to be very clicky. They need to be big and chunky so they're easy to grab, not cute little things that are hard to find when you're wearing gloves in the wintertime, whatever. And yeah, audio tones. Internally, I want to use the ARM Cortex A series microprocessors. I have looked at ESP32s. I have one. I'm not super impressed with what all it comes with, and I think that going to a full microprocessor um, would be better. One of the things you can get with that very easily is a GPU. You can use OpenGL. So we're talking about hardware accelerated graphics so that the interface is always smooth and responsive. In order to use that kind of hardware, you really need a real operating system underneath. This won't be Linux as in Ubuntu. This will be Linux as in an embedded Linux that is built just for this hardware. We'll use probably something called Open Embedded, but I'm not sure yet. And then the software that runs in here, I don't know yet. I would like to avoid X Windows, X11, Wayland, all of that, and just write directly to the OpenGL API, but I haven't gotten far enough to really assess how much work that would take. Now, the other side of product A, we were just looking at the user interface. Now we're looking at the ADARS module. That's the sensor collection, the data collection, and processing. We'll do 3 barometers. That gives us airspeed, vertical speed, altitude, and as I mentioned before, angle of attack. The third barometer is not something that's included on the products that I showed earlier, Garmin, Idaho Avionics, and Canardia. We'll have a 9-degree of freedom IMU, including magnetic heading, and a G meter built in. That gives us attitude, magnetic heading, turn coordinator, and G meter. And then we'll have 2 temperature sensors, maybe 3, because those are just really wires that plug into the back. So there's a lot of real estate, there's a lot of physical space for those. Temperature sensors can give us things like true airspeed based on indicated airspeed and density altitude based on pressure, altitude, and uh, so there's more here that can happen just by adding a couple of extra sensors and making sure that the hardware is very capable so that the software can evolve with time. Uh, the hardware behind this for data ingestion, I'd like to use the ARM Cortex M series microcontrollers. There'll be no operating system running in this side of the device. That's to keep things simple and correct and reliable. The software will be written in C, which is generally known for it's a very low level uh, programming language. But we don't have to write a lot of code there because again, we're going to keep it simple. This side of this module within the product is really there to collect data no matter what the UI is doing, to collect it reliably, to collect it consistently. That's the whole product. That's what I'm working on next. So look at the shorts that I've been posting, and you'll see what I've been doing lately and how far I've come along so far, mostly on the 8 hours module. Thanks for watching.